Hello, it's lecture 36, stat134. Remember on Wednesday you have your final quiz. Last time, which was a long time ago, we were doing section 6.3 on conditional density, which remember is essentially a slice of the joint distribution at x is x. And an example of the conditional density comes up in Bayesian statistics when we can update the distribution of a parameter of a distribution, for example, theta of Poisson theta. So let's suppose that theta is given the distribution of gamma r lambda in the prior, and we collect data n1 to nm, which are IID Poisson theta, and we wish to identify what the posterior is going to be. So remember that gamma and Poisson are conjugate pairs, so we shouldn't be surprised that the posterior will be the same distribution as the prior, which is gamma. So the likelihood factorizes, and we're given the Poisson formula for each of these factors. Furthermore, the prior has the gamma distribution, and when we combine these, we see the variable part of a gamma, which we can then identify is the posterior distribution. Today, what we're going to do is we're going to start section 6.4 on covariance of the covariance and the variance of sum, and as well correlation. So tentatively we're going to finish the book this week or the very beginning of next week, and then review for the final. The final is on Thursday, December 13th, and the room will be announced. So when we have a sum of two random variables, the variance S of this x plus y is defined as the expectation of the deviation squared, and the deviation of that sum can be broken up as the deviation of x plus the deviation of y. So the variance of S then is the expectation of the deviation of x plus the deviation of y squared, which when you FOIL, you get expectation of the deviation of x squared plus the expectation of the deviation of y squared plus 2 times expectation of deviation x deviation y. So the first two terms are variance of x plus variance of y, and then we get a covariance term. So the definition of covariance is the deviation, expectation of the deviation of x times the deviation of y. And this has bilinearity properties, which you guys showed in class. I don't have anything to say about that. So these bilinearity properties generalize as shown here, and an important result proved at the end of the lecture is that the covariance of xy is the expectation of xy minus expectation of x expectation of y. And it's easy to confirm that covariance is really just a generalization of variance to having when you have two random variables. So in the case when x and y are the same random variable, you just get the variance of x. The covariance of xy is the same as the covariance of yx. You can just see that from the symmetry of x and y in the theorem above. And the covariance of x and a constant is 0. Again, you can see that following very easily from the theorem above. So then I asked you to practice your bilinearity skills and simplify this covariance, and you did that beautifully. I don't really have anything to say here. Recall that if x and y are independent, then the expectation of xy is equal to the expectation of x times the expectation of y. And so that implies that if x and y are independent, the covariance of xy is 0. So that means that the variance of x plus y, if x and y are independent, is just the variance of x plus the variance of y, which is very nice. And if x1 to xn are identically distributed, then the variance of the sum is the covariance of those sums for the sums in each spot here, right? Because if the sum was called y, then the variance of y would be the covariance of y comma y. So we have this equation here, and this, by the bilinearity term, this will be the covariance of n squared terms. Rather, it'll be a sum of n squared covariance terms. And these n squared covariance terms appear in this variance covariance matrix that I've written out here. And the diagonal terms of this matrix are the variances, and the off diagonals are the covariances, and all the variances are the same, and the covariances are the same. So we just get n variance x1 plus n times n minus 1 covariance x1, x2. Now, another important example is drawing from a population. So say that x1 to x capital N is a population, so it's numbers in a box, and say that the population mean is mu and the population SD is sigma. We draw n of these numbers without replacement. This is called a simple random sample, and this defines n random variables x1 to xn. Let Sn be the sample mean. We're going to find the expectation of Sn and the variance of Sn. So the expectation of Sn is very easy. We just get n times mu. The variance of Sn will be n sigma squared plus n times n minus 1 covariance x1, x2. But we need to find what covariance of x1, x2 is. So there's a trick, and that is to take a census. So we're going to pull out all the elements of our population. And of course, then the sample mean will always be the same. So the variance of that sample mean will be 0. So we have 0 n sigma squared plus n minus 1 covariance x1, x2, where here n is capital N. And then we can solve for covariance x1, x2, and we see it's equal to minus sigma squared over n minus 1, and hence the variance of Sn is n sigma squared times this correction factor, n minus little n over big N minus 1. We've seen this correction factor before when we compare, for example, the variance of the binomial to the variance of a hypergeometric. Then we get the variance of the binomial is n sigma squared, where sigma squared is pq, because that is the variance of an indicator. And the hypergeometric is essentially n sigma squared times this correction factor. So then we moved on to correlation, which is covariance divided by SDX over SDY. And so the SDX and SDY, they're just numbers, and they can go into your expectations. So we see that correlation is just the expectation of x and y in standard units, where the x's we subtract the mean and divide by the standard deviation. And so say that you have a scatter diagram, okay? So these points in the plane each have a xy coordinate, you can divide up the plane into 4 quadrants given by the expectation of x and expectation of y as being your axes. And we see that in the first quadrant, the product of the x and y in standard units is positive. In the second quadrant, it's negative. In the third quadrant, it's positive, and in the fourth quadrant, it's negative. So if you look in this second picture here, you can see that a scatter diagram with a positive correlation has mostly positive x star y stars, and so the expectation of this, which is just the average, because each point is equally likely, we're going to get mostly positive numbers, and so we get a positive R. If it's downward sloping, then we'll have a negative correlation because we have mostly negative x star y star products. So then I gave you this problem to do. Suppose the sum of k exchangeable identically distributed random variables is a constant. Find the correlation of n1 and n2. So what I wanted you to do here was take the variance of both sides, since you know the variance of c is 0, and then use the fact that this is just k times the variance of n1 plus k times k minus 1, the covariance of n1 and 2. You can then solve this for the covariance of n1 and 2. And to find the correlation, now we divide by SD n1 and SD n2, but n1 and n2 are identically distributed, so they have the same SD, so their product is just the variance of n1, so that will cancel from above, and we get minus 1 over k minus 1. We then finished with a concept test. So consider a Poisson lambda process. TR is gamma R lambda, be the rth arrival time. Covariance of T1, T3 equals. So, the main idea here is that, of course, T1 and T3 are correlated, but T1 and T3 minus T1 are independent. So their covariance is 0 here. And so using the bilinearity, then we can solve for a covariance of T1, T3 is the variance of T1, and the variance of T1 is 1 over lambda squared, because R is 1. And then for the second problem, we needed to find the correlation, so we just divided by SD T1 and SD T3, and that just gave us square root of 1 over 3. So that was the show for today. Here, just in the appendix, is a quick proof of the covariance of xy is the expectation of xy minus expectation of x, expectation of y. Make sure you understand this proof, but it's very straightforward. I'll see you next time. Bye-bye.